Okay, yeah, I'll start with my last lecture. I just put the link to the Dropbox again in the chat with the most up-to-date notes. Yeah. So what we're talking about today, sort of in the final lecture, is first what we'll do is I'll explain why we have also an avoidance principle for Brakke flows. Yeah. There's a maximum principle. And then I'll relate it to a different notion of weak solutions to mean curvature flow. I'll relate it to Levelset flow. Yeah? Okay, we'll be doing today. Now, first to the avoidance principle. So here's the first theorem. It's a barrier principle. And since it's not so well known that you can also have a barrier principle for in curvature flow in higher codimension, let me do this in any codimension. Yeah? So suppose M is the space-time support. Of an m-dimensional integral Brakke flow. We haven't defined this exactly, but all the definitions work the same way. Yeah? Ut, t in some interval I, we can even do it just locally in an open set U in R capital N. Yeah? Then let U from U cross I into R be a smooth function such that at the point x0, t0, we have du by dt is less than, I'll define this, what is the m trace of the Hessian of u, where nabla 2 is the spatial ambient Hessian, and trace m is the sum of the smallest m eigenvalues. Yeah? So you can also see this as you take any trace over any m-dimensional subspace, and then you minimize over all m-dimensional subspaces. Yeah? But since the Hessian is always symmetric, you can just take the eigenvalues. Yeah? Then, if you restrict U to this space-time supporter prior to t less than t0, then this cannot have a local maximum at t0 at x0 t0. Okay. So this means if you have you can use function as barriers even for higher codimension mean curvature flow. Let's do a proof. So assume otherwise. So we have a local maximum there. So what we can assume that M is the same as M intersected t less than t0. We just cut it off. And that U restricted to M has a strict local maximum. At x0, t0. If not, otherwise, replace U by U minus x distance x to x0 to the power 4 minus t0 minus t squared. You see, this makes this would make it into a strict local maximum, but it doesn't change the spatial second derivatives or the first time derivatives at that point. Now we just do a higher order perturbation to make it into a strict local maximum. Okay, so that's what we can assume. Now we take PR. So this is this parabolic cylinder, backwards parabolic cylinder of radius r at x0. So this is the ball of radius r at x0 cross t0 minus r squared t0. Yeah? Take the you contain the last time. Now choose r positive, small enough such that t0 minus r squared is past the initial time of the flow. Okay, we want to have that u restricted to m intersected closure of r has a maximum at x0, t0 and nowhere else. And but we can also assume that we have du by dt is less than this m trace of the Hessian of u on the closure of PR. Huh? It's just all localizing everything. By adding a constant, we can assume that we have u of m intersected p bar without p. So this is just a parabolic boundary that here it's less than 0 and it's less than u is strictly positive. Yeah? Okay, we're just shifting it a little bit. And then we let u plus is the maximum of u and 0 and plug again as before u plus to the 4 into the definition of Brakke flow. Okay, let's see what is important now. So that function here, that function u plus is always 0 on this parabolic boundary. Huh? Remember, this is our assumption here, but it's before negative. Yeah, so the positive part, if you take on the positive parts, it's 0. So we get, what we get here, we get 0 is less or equal than integral over br, u plus to the 4th, d mu t0, but that's the same thing as br, u plus to the 4th, d mu t0 minus br minus r squared. Yeah, this is just because, you know, this is all 0 here on there. Now we just put in the definition. So this is d dt u plus to the 4th plus mean curvature grad u plus to the 4th. Sorry, this minus mean curvature squared u plus to the 4th d mu t dt. Okay, that's less or equal than. Now we again drop the mean curvature squared term and do integration by parts. So we have du by dt. Now we have a minus the divergence over our flow at time t, gradient of u plus to the 4th. d mu t dt. Okay, now let's compute this. Okay, so it gets 4 times u plus cubed du plus by dt. You can even take du by dt. Yeah? So du by dt here minus 3u plus squared tangential gradient of u plus squared. Yeah? That's just when the divergence hits the other factor minus u plus cubed divergence over mt gradient u plus You can even take gradient u here. Huh? Gradient u. Yeah. Now d mu t dt. Okay, but you know we can drop this term, and we see that we get then here t0 minus r squared t0 here for u plus cubed du by dt u plus minus the m trace of the Hessian of u, and we can even erase the plus here. We don't need the plus here. Yeah. d mu t dt. Okay, because we have the u plus already here. We're already cutting out, and that is strictly less than 0. Yeah? So we get a contradiction that proves this theorem. Okay. So it's just sort of strong maximum principle. Yeah? Just using the integral representation to localize that. Okay, so this is this interesting thing. So what do we get as a consequence? Yeah. So let's take the next theorem here. Call this the weak barrier principle. No, this it's the barrier principle. Let's call this the weak barrier principle. Okay, so let's relate this to hypersurfaces. Yeah, let M be the space-time support of an. Now let's do it in any codimension, an m-dimensional integral Brakke flow. Just because I think it's important for people to see that you can do barrier principles even in higher codimension. Suppose t maps to n of t is a one parameter family of domains in U, such that we want to have that the boundary is a smooth one parameter family of hypersurfaces. Now what we assume, assume that m of t that this is always contained in n of t. Yeah? So more or less we think of our flow is contained in a smooth family of domains, yeah. And now we assume that it happens that the flow touches the boundary of the domain, yeah. If p is in m of tau intersected dn of tau, then the speed p of v tau is always greater or equal than hm of p tau, where v of p tau is the speed of dn of tau at p. So this is the normal speed, and v times nu, and it's p. I'll say, let's do this. Sorry. At p in the inward direction nu, and hm is the sum of the m smallest principal curvatures of dn. Okay, so what does this mean? This means this whole thing cannot happen. This whole thing cannot happen if our normal speed is slower than the sum of the smallest m-principal curvatures at the boundary point. Or, for example, if you take mean curvature, codimension 1, yeah, what would this be? This would be the mean curvature. If our speed is smaller than the mean curvature, then there can't be a touching point. Yeah, it can never touch the boundary. Okay. Okay, now let's do the proof. And proof is more or less, I guess, pretty clear. We use the distance function to the boundary. Let f from u to r be defined by f of xt is minus the distance to dnt for x in n of t and the distance to x dn of t if x is not in n of t. Yeah? Okay, so we take the distance function negative to the inside. Yeah, and let E1 up to En minus 1 denote principal curvature directions of dn of t at p. Okay. Now then, what is the important thing? I guess you all have done the computation. Then we have En up to En minus 1 inward unit normal is an ON basis at P. Yeah, and we compute. So this is the important thing. If you take the Hessian of the distance function, you get exactly the second fundamental form. So you get here kappa 1 up to kappa n minus 1, and here you get 0. Okay. Now we set u is e to the alpha f. Okay. Now, just as a good test function, we've seen this all in PDEs, yeah. Then what you have du is just alpha e to the alpha f times df. So what do we get? We get that the Hessian of u is alpha squared e to the alpha f df transpose df plus alpha e to the alpha f d squared f. Okay. What do we get from there? That the eigenvalues of du of the Hessian of u at p, yeah, note we have u of p is equal to 1 because f is 0. Are, what are they? They're just alpha times kappa 1, alpha times kappa n minus 1, and alpha squared. Because we get here this factor 1. F is the distance function. So that gradient has length 1. So we get alpha squared here. But you see now, the idea is if you make alpha very big, you can make this here much bigger than any of the other ones here. That's the trick. So for alpha sufficiently large, we see that the M trace of the Hessian of u at P is exactly alpha times HM. Or, on the other hand, we know that du by dt, along the, at that point, what it is alpha e to the alpha f, df by dt, and that is just alpha times v at pt. If you take the distance function, if you change the hypersurface in time, that gives you always the normal speed, the time derivative. Now, by assumption, f restricted to m has a maximum. It's the first time it's touching at pt, maximum at pt. So the conclusion follows from the barrier principle. Okay. Okay, so this is nice. This means we can use actually boundaries as barriers for even for Brakke flows in any codimension, if they move in the right way. Okay, now let's specialize to codimension 1 here. So here's the theorem. This is the barrier principle for hypersurfaces. Okay, now this is really sort of, you compare with mean curvature flow. Let M be the space-time support of an n-dimensional integral Brakke flow in Rn+1. And just as a comment, yeah, this all, as you see, this is also always something local, so you can make the same thing work in a Riemannian manifold, yeah. And let mt is just a slice at time t of the support, yeah. And m denote the t slice, t time slice of m. Suppose t maps to n of t is a one parameter family of closed domains such that t maps to the boundary is a smooth, so what as we think of a family of hypersurfaces moving which have interior, it's a smooth one parameter family of hypersurfaces. Now let's assume that dn of t is compact and connected. Yeah, just look at one connected component, yeah. And we want to have that the inwards normal speed, yeah, is less than the mean curvature. Yeah? So our solutions are not moving, are slower than mean curvature flow, yeah? Our barriers. Yeah? Now suppose that M0 is contained in N0 and that it's not all of the boundary, yeah? And that dn of 0 without M0 is non-empty. Then m of t is contained in the interior of n of t for t positive. Yeah? Okay, so this is really the barrier principle. Okay. So here, sort of, first we prove a little lemma. Assumptions as above. If m of 0 is really contained in n of 0, so it's in the open set, yeah, then m of t is contained in n of t. Yeah, so I just don't want to do the strict case. Yeah, here's the proof. Huh? Let n epsilon of t be the region with dn epsilon of 0 is dn of 0, which flows with speed. We just make it a bit slower, mean curvature minus epsilon. Okay. Now, if f for epsilon sufficiently small, the flow will be smooth. Comparable to the one of the definition of n of t, or you can just do it for a very short time. That's enough, and let's always push it inwards. Yeah, and then we can apply the weak maximum principle. So barrier principle from before, and let epsilon go to 0. And we're done. Okay, and here's the proof of the theorem. Okay, since we assume, so there's even the strong maximum principle, that dn of 0 has some points which are disjoint. From M0, we can push it a little bit inwards, yeah. We may push dn of 0 slightly inwards. At these points, yeah. So we have here dn of 0. Now assume here is our, like this is m of 0. Okay, and then we can just, instead of taking this here, we can just push it a little bit inwards here. And the idea is, if we let this now here, the violet curve, the violet boundary flow, it immediately separates from the black flow, just by smooth, strong maximum principle. To find a new set, hat of 0 with dn hat of 0 smooth, and m of 0 is contained in n hat of 0, but thus it's not equal to n of 0. Then what we do is flow dn hat of 0 by mean curvature flow. It will remain smooth for a short time. For a short time, by classical maximum principle. So maximum principle, we have that dn of t and dn hat of t immediately become disjoint. It's peeling off everywhere. Then apply the lemma. Applying the lemma to n hat of t yields the result. Okay. Okay. So this just means what we have done so far is says, okay, if any Brakke flow satisfies an avoidance principle with respect to a smooth mean curvature flow in codimension 1. Huh? So this means if you take a smooth solution and a Brakke flow and assume they're disjoint, so they stay disjoint. Are there any questions regarding what we've done so far? Okay. I just said this orally, the marks there. So this only works in codimension 1 here, yeah. But at least you can see something like, I put this in the notes, yeah. If you have higher codimension mean curvature flow, some surfaces are still barriers. For example, if you take shrinking spheres with the right speed, it uses that they're totally umbilic, yeah, then they still act as barriers from the inside and from the outside. Yeah? So even in higher codimension, you still have, for example, shrinking barriers or planes. They are still barriers for curve shortening flow or mean curvature flow in general. Okay, now we want to, so what we haven't shown yet, that two Brakke flows avoid each other. Okay, so we have only shown that a smooth flow and a Brakke flow avoid each other. Now we need one technical lemma here from Ilmanen. So this is the following lemma. And I'll draw a picture. That's extremely helpful. This is called the C11 interposition lemma. To Ilmanen. References in the notes. Says the following thing, also works in a manifold given disjoint closed sets x and y in Rn, or maybe say Rn plus 1 here at the moment. X is compact. Then there exists a compact C11 hypersurface Q and a bounded open set U such that the following is true. We have X is contained in U, Q is the boundary of U, and Y is in Rn plus 1 without U. And here's the second one, that's the important one. This hypersurface exactly bisects the distance between X and Y. So the distance from X to Q plus the distance from Q to Y is the distance from X to Y. Okay, let's draw a picture here. Okay, so take, let's say this is our set X. Okay, then let's take this here to be the set Y. This is the set Y. If there's something down there. Okay, let's close it here. Something like this, for example. Now, what does this mean? So what you do here, you take, for example, R to be half the distance. So let's take tubular neighborhood of radius R. So, for example, take now R is distance X, Y divided by 2. Let's draw the tubular neighborhoods around with R half around X. Okay, and let's do this to the inside here too. Of this one here. So this is maybe here. Here it lifts off. Maybe here there's another touching point. That was not good. Like this. Here. Here. And this looks like this. Okay, now let's see what would be kind of closest sort of connections here. Here would be maybe one. Here would be one. Maybe here would be one, and here would be another one. Okay, And now the idea is what Ilmanen shows here. Yeah, but you see the idea is at all these points, you have here from here, you have a ball touching of radius r. Yeah? Always these balls touching of radius r on both sides. Okay, so this is why you can imagine that the C11 condition is something attainable. Yeah? What the Ilmanen shows is you can put this hypersurface Q in here. Yeah? You can find something in here. So this is Q. And yeah, here the interior here. This is U. Okay. Okay, so the important thing is, so the distance from X to Q plus from Q to Y is the same as the distance from X to Y. Are there any questions with this? So this is extremely helpful, huh? Because from this immediately we get the following avoidance theorem for avoidance for codimension 1 Brakke flows.
There's a question in the chat.
Yeah. Okay.
Ask whether you can control the curvature of the hypersurface.
Yes, the curvature is 1 over r at most, I think. That's what you can do. So I think sort of in the between places, you can make sure that the curvature is at least sort of not more than a multiple of 1 over r. Huh? Or, yeah. Okay, so here's the avoidance for codimension 1 Brakke flows. That now here script M1 and script M2, B2, n-dimensional integral Brakke flows on Rn plus 1 defined for T positive and such that, okay, the support of M1 at time 0 is compact. One of them you need to be compact, and you want to have the supports initially disjoint, and support of M1 at 0 intersected the support of M2 at 0 is empty, then you get exactly that the distances has to be increasing in time. No, it should be comma here. There's a typo in the notes. Comma support 2 of t is strictly increasing. Okay, so let's do the proof here. Using big spheres as barriers, we see that the support of Fm1 at time t is compact for all positive times. Yeah? Now we know that we can take smooth hypersurfaces as smooth mean curvature flows as barriers, especially big spheres. So this stays contact, yeah, by the C11 interposition lemma. We can choose a domain N such that the boundary is a C11 hypersurface. Such that, so what do we get here? So we can assume that the support of M1 at 0 is in the interior of N, and the support of M2 at 0 is in the complement. Okay. And here, now here's the important thing. The distance of the support of M1 at 0 to dn plus the distance of the support of M2 at 0 to n to dn is equal to the distance of the support of M1 of 0 to the support of M2 at 0. Okay, that's exactly what we did before, huh? Now let n of t be the region with dn of 0 is dn flowing by mean curvature. We need this only for a short time, huh? Since we have that dn is C11, this will exist for a short time. Actually, even C1 would have been enough, yeah? Or small Lipschitz, yeah? We can then use theorem 6.3, yeah? Because the flow will be smooth for every positive time, yeah? So we can use these as barriers to see that. Okay, so what do we get? Yeah? We have that the distance at time 0 I do to intersect many typos here. Support M2 at 0. Now we have this is the same as the distance of the support M1 at 0, dn plus the distance of dn to the support M2 at 0. And okay, but this is now each of these here to this, we let this evolve here. Huh? So here the distances are increasing. This is less or equal, or even strictly now, huh? It's bigger than the distance of support of M1 at t, dn at t, plus distance dn at t, support M2 at t. Okay, and sure, this is less or equal to the distance of the support of 1 at t to the support M2 at t. Okay, for t positive. Okay, so this means that gives us that any two Brakke flows always avoid each other. So this is a very helpful lemma to know, and more or less this works for any kind of flow as long as you have an avoidance principle. And you can start from C11 initial data. Okay, any questions here? Okay, then let's sort of start with Levelset flow. Okay, Levelset flow is more or less a weak solution to mean curvature flow, which is only based on the avoidance principle. So it's okay. So let's do a definition. What is a weak theoretic subsolution? So a family delta t positive of closed sets in Rn plus 1 is a set theoretic subsolution of mean curvature flow provided, so what do we want to have? For any family, so we want to have that it avoids any smooth solution, any family mt, t in t0, t1 of smooth closed hypersurfaces moving by mean curvature. If we have that, if they're initially disjoint, we want to have the barriers, the smooth surface always be compact, so there the compactness there. This implies that we are disjoint in future. Okay, yeah. Or equivalently, since we are in Rn, yeah, and we have translation in and around, this gives us that the distance is increasing in time. Okay, yeah. So this gives equivalence, yeah. Now, what you see, we can do now the same thing. We can use the C11 interposition lemma to show that two subsolutions, two set theoretic subsolutions avoid each other. Yeah? Because we can just put, again, a C11 hypersurface in between, like before, and argue the same way, yeah? Using the C11 interposition lemma. As in the proof of the avoidance principle. For Brakke flows, we see, what do we get? You get the following lemma. This is avoidance for set theoretic subsolutions. And we say, okay, let delta t, t positive, gamma t, t positive, be set theoretic subsolutions of mean curvature flow. In Rn+1, so more or less anything that moves too fast or faster than mean curvature flow at the boundary, or if it's something it moves too fast, if you have a full set, then the boundary moves too fast, in Rn+1, and we assume that they initially are disjoint, and you want to have gamma 0 is compact, and we only need to use it from the initial condition, then the distance between them both is non-decreasing. It's even strictly non-decreasing. Okay, so this is nice, huh? Now, that's what we get. Here's a little note. See, if you take the union of two subsolutions, that's again a subsolution, yeah? Note, the union of two subsolutions is again a subsolution. Yeah, that's like for the Laplace equation, yeah? If you have two subsolutions, you take the maximum of two subsolutions, then this is again a subsolution, huh? Here's the same thing, yeah? And here's the definition. What is the Levelset flow? Okay, so we take a closed set in Rn plus 1. The Levelset flow Ft of delta is the maximal, is the maximal set theoretic subsolution starting at lambda, which is delta, which you say is delta 0, that's F0 of delta. Okay, now you just take the union of all possible subsolutions. Here just some basic properties, yeah. The proposition is the basic properties. This just out, let me just state them. Although I think we still have a bit enough time. We can do this, yeah. So here's the Levelset flow is well defined and unique and has the following properties. So the first thing, we have the semigroup property. So we have F0 of delta is delta. So first the identity, f of t plus t prime is delta, and f, so that we just have here ft prime of delta. So we can first move, this is just this normal semigroup property, then it commutes with translations. Ft of delta plus x is ft of delta plus x. And we have containment. Sure. If we have delta is contained in delta prime, then ft of delta is contained in ft of delta prime, yeah? Because it's just everything is done by avoidance. Yeah? What is the, let's do the proof. Yeah? As we've seen, it's as we have seen that by translation invariance, which is note that we can write the Levelset solution, the Levelset flow as follows. Now we can just say ft prime of delta is just the union over all delta at t prime, such that this is the subsolution. Right. And we take the closure of that. See? So the Levelset flow exists and is unique. Okay, and then all these properties just follow, all the properties follow from existence and uniqueness. And translation invariance of mean curvature flow in Rn plus 1. Yeah? Okay, are there any questions so far? Okay, now get towards the end of it. So let's relate this. You might have heard about this level set flow as defined by Evans and Sprague and Chen, Giga, and Goto. Huh? They define it differently. Relation to level set flow. That's why it's actually called level set flow. Huh? As defined by Evans and Sprague or Chen, Giga, and Goto. The references are in the notes. Huh? Okay, so what do? Huh? They consider a viscosity solution. So you do again tangency and with test functions, yeah, and do this on test function. They consider a viscosity solution to the following equation. Let's call this star. Huh? So you define dTu is equal to delta ij minus nu I nu j Hessian ij of u on Rn plus 1 cross 0 infinity, and you specify u at time 0 to be some function f. Okay. What is nu? Well, nu is just the normal to the level set. Du by mod du. When this is defined, when it's not defined, they have to do a little bit different trick. When you don't have, when the gradient vanishes, yeah. So the important thing is so they show that in the viscosity sense, you can always solve this equation. You can find a solution, and you can even show the solution is unique. Yeah. But the important thing when u is smooth, and du is not equal to 0, then star says, yeah, that all the levels, that the level sets of u are simultaneously moving by mean curvature. Or think it the other way around. Think you have like a foliation of hypersurfaces, and you let them all move by mean curvature flow as well. And now you assign to each hypersurface a different sort of parameter, and then this gives you a function u. And now what they show is if f is continuous and all but at most one, so more or less, you can have one non-compact level set, one of the level sets of f are non-compact, then there exists a unique u weakly solving star. I gave the reference where this is. Now, what they also show that the family of level sets gamma at, so this is just x u of xt is equal to a, for t positive is unique. They say that they show it does not depend on sort of what function f I've used initially, is unique and is called the level set flow. of F inverse of A. Okay. Now one can check, huh? By definition, by the definition of solutions to star, that uses tangency with test functions, usually viscosity techniques, yeah, that one can one can check, yeah, sorry, a level set, in this definition, yeah, a level set flow on Rn plus 1 is a set theoretic subsolution of mean curvature flow. So all these levels, yeah, here, if you take any of these, you can check these are subsolutions to mean curvature flow. But you see all these levels always avoid each other, and they always form they always sort of foliate the whole space. Huh? Okay. Now here, note the following now. Huh? Note any set theoretic subsolution that is contained within a level set flow at t equal to 0, yeah, must remain contained in it. Why is this the case? Otherwise, it would run, assume it's not contained, so it has to sort of leave that, but then it would run into one of the other levels of the level set flow. But these are all weak subsolutions, and we know they avoid each other, so you get a contradiction. Yeah. Otherwise, it would run into some of the other level sets of U, violating the avoidance of set theoretic subsolutions. Yeah. So the idea is, since you have this foliation of subsolutions, yeah, that gives you that this is kind of already the maximal one. Yeah. Okay, so this gives you, this shows equivalence. Of both definitions. So this means this maximal set theoretic subsolution is exactly the level set flow. Okay, now let's relate this to Brakke flow in the very end here now. Okay. Remember, we have seen that Brakke flows are a set theoretic subsolution, so we have the following lemma. Let M be the space-time support of an n-dimensional integral Brakke flow on Rn plus 1, then the family of sets MT, yeah, just these time slices are a set theoretic subsolution to mean curvature flow. Okay, now what is the corollary of this? Now we take a Brakke flow, script m, yeah, be an n-dimensional integral Brakke flow. On our n plus 1 for t greater or equals than 0, and we take a Levelset flow. And if the support of the initial measure is contained in gamma 0, then we get that the support of mu t is contained in gamma t for all t greater than 0. Okay, so in some sense, more or less, what you have to understand here, in some sense, this Levelset flow is kind of, can be seen in some sense not as the union of all possible Brakke flows, or in some sense that's some of the hope, or at least it can be used as some kind of measure of uniqueness. Yeah. Okay, so note, we can thus use the Levelset flow to characterize possible non-uniqueness of Brakke flows. Somehow, if the Levelset flow somehow is tight enough, then we can use this to somehow rule out that the Brakke flow is non-unique. Yeah? So what we need for this is, the notion used for this is called non-fattening. Yeah? Okay, so what is non-fattening? Here's the definition, and I'll be coming to an end very soon. Yeah? A bit faster than I thought. A Levelset flow, gamma t, Levelset flow is called non-fattening provided what is the case? This is the weakest definition. So what you take gamma t cross t, and most you look at the space-time track of this Levelset flow. So you take the union over all positive times. So see, this is a subset of Rn plus 1 cross R, and now you ask that the n plus 1 dimensional Hausdorff measure of this is 0. Okay, so that's rather weak. So here's the important note. So this is really sort of, we're looking at, so this is our initial one, and then we look at sort of all these ones stacked on top of each other. Okay. Now, and if this whole sort of thing in space-time has Hn plus 1 measure 0, so what is this note? Here's the important thing. But note, these Levelset flows, they foliate Rn plus 1 cross R. And if you have a foliation, then at most countably many of sets in a foliation can have measure bigger than 0, because you have uncountably many Levelsets. And if more than countably many carry something, then that is sort of, that contradicts the local finiteness of the ambient measure. Okay, so note, this implies that for the Levelset flow, as defined by Evans-Prock, or Chengi-Kagoto, that at most countably many levels. Sorry, I think this should, there's a typo here, it's an important typo. Just thinking about it. So this should be this here has to be hn plus 2. No? No? Otherwise, you see, you want to have that it doesn't have really full measure in the ambient space. Otherwise, you don't get this finiteness. It's a typo here. In the notes, most countably many levels u of xt equal to a could be fattening. Okay. Now, what is the important thing? This means non-fattening is a generic condition. No? Is a generic condition. Okay. Now, but the interesting thing, this non-fattening is actually, you can make it much stronger. Yeah? The following equivalence is known. I gave the reference, yeah. If you know that the initial measure has finite hn measure, the initial set you start with, then the Levelset flow gamma t is non-fattening if and only if we know that the n-dimensional Hausdorff measure of gamma t is finite for all t positive. Okay. So really fattening, you know, we looked at this here in space-time, yeah. So there's a much stronger statement that actually is equivalent to that. Okay. Now, what is the idea of this? And this is sort of something we won't be able to cover today anymore. But the idea is you can start using this here to characterize uniqueness for mean curvature flow. Here's this important recent work, yeah. For example, by work of Hershkovits and White. Right, I'll put the reference in, and the resolution of the mean convex neighborhood conjecture. The people have heard about this, yeah, by Choi-Haslhofer-Hershkovits and Choi-Haslhofer just recently. Hershkovits-White. Yeah. One knows that if a Levelset flow, that's how they define it. If a Levelset flow has only spherical, so you have only tangent flows more or less, which are shrinking spheres, or neck pinch singularities, i.e. modeled on on shrinking cylinders, that's n minus 1 cos r, then the Levelset flow is non-fattening. And you can also show that the Brakke flow then also is unique, and the corresponding Brakke flow is unique. Okay, put a bit more details are in the notes. Just a tiny bit more. Okay, so this means you can start then. So the idea is by using this Levelset flow, that is a tool to understand when Brakke flows through singularities can become non-unique. So that's one of the ideas of Levelset flows. In some sense, these Levelset flows capture all possible evolutions past singularities. Okay, for example, one can show that if you have this Brakke flow, or this Levelset flow, assume it fattens up, then you can still show that sort of the boundaries, like the inner boundary and the outer boundary of this fattened up flow, if you have non-unique evolutions, that they still are Brakke flows by itself. Yeah? So that's one way of trying to understand these things. Okay, that's what I wanted to cover. Yeah, thank you all very much for your attention. Are there any questions?
No questions in the room. Apparently, no questions in the chat either.
Something page 18. So what is page 18?
Page 18.
You mean page 18 in the notes?
Ah, yes.
Okay, let me go back to the notes. Okay. Corollary 4.3. Okay, so what is the question about corollary 4.3? So this was this. Okay. So this is about this definition of a varifold and about the tangent space of a varifold. Is that right, or? Okay. Okay. Mm-hmm. You see, you want this, your set S is just the intersection S. And you just look at the tangent space of this. Yeah, but you have to take the, you see that the dimension of the C1 manifolds has to be the same dimension of the set you want to look at. See? You see, you don't look at something lower dimensional, like it's the intersection of a plane with a cylinder. Yeah, that would be, for example, here one dimension lower. Yeah, you want to look at the set, and you sort of just extend the set in different possible ways. And the idea is that it does not depend on in what sense I extend the set to a C1 submanifold. Okay. It does not depend what kind of extension I take. Yeah. If there are more questions, please write me an email. Yeah, I'm happy to answer emails.
Okay. No other question? Okay, let us thank Felix for beautiful lectures and very precise notes and so on. I just recall you that Felix will give a lecture in the third week of our school, which is a workshop actually. And if I remember well, it's on Tuesday morning at 11 Paris time.
Yeah.
Thanks a lot, Felix. And,
thank you.
Happy to see you.
Bye, everyone.
Bye.